Have you ever gazed up at the night sky and wondered why space is so dark? The question seems simple, but it's a cosmic conundrum that has puzzled astronomers and philosophers for centuries. It brings us face to face with the mysteries of the universe, probing the very essence of our existence. Imagine the universe, a vast expanse seemingly infinite, brimming with countless stars and galaxies. Each star, a radiant point of light, millions and billions of them scattered across the cosmos. Yet when we look up at the night sky, we don't see a bright canvas painted with the light of these celestial bodies. Instead, we are greeted with an endless abyss of darkness, sprinkled with tiny specks of light. It's a paradox, an enigma, a riddle wrapped in the mystery of the cosmos. This paradox is so profound that it has a name, Olbers's paradox, named after the German astronomer Heinrich Wilhelm Olbers, who popularized it in the 19th century. But Olbers wasn't the first to ponder this cosmic puzzle. The riddle of the dark night sky has been contemplated by thinkers and stargazers since ancient times. Yet, Olbers' paradox, as we call it today, succinctly captures the essence of this cosmic conundrum. So, let's delve deeper into this mystery. If the universe is indeed infinite, populated with an infinite number of stars, shouldn't the night sky be ablaze with their collective light? Shouldn't every point in the sky hold a star, and thus be as bright as the surface of a star? Why then does the darkness dominate? As we embark on this cosmic journey, we'll explore the mysteries of light, the nature of the universe, and the theories that try to unravel this paradox. We'll delve into the heart of darkness, seeking to illuminate the shadows that shroud the cosmos. If the universe is filled with stars, why doesn't their light fill the entire sky? As we journey through the cosmos, we'll seek to answer this question, unraveling the mystery of the dark night sky. To crack this cosmic conundrum, we first need to understand how light works. Picture light as a wave zipping through space. It's a form of energy that our eyes can perceive. Light is part of a larger family of waves known as the electromagnetic spectrum, which also includes X-rays, microwaves, and radio waves. But for our purposes, we're most interested in visible light. Now, light doesn't just meander along at a leisurely pace. It's the ultimate speedster, racing away at an astonishing 186,000 miles per second. That's so fast that in the blink of an eye, light can zip around Earth 7.5 times. This speed is so crucial that it's become a fundamental constant in physics, often denoted by the letter c. And it's this speed that gives rise to the concept of light years, a measure of astronomical distances. A light year is the distance that light travels in a year. Just imagine, in 1 year, light can travel about 6 trillion miles. But here's where things get really interesting. When we gaze up at the stars, we're not seeing them as they are right now. We're seeing them as they were when that light left them. For some nearby stars, that might be just a few years ago. For others, it could be hundreds, thousands, even millions of years in the past. And what about galaxies that are billions of light years away? The light from these galaxies started its journey billions of years ago, and some of that light is still en route, still yet to reach us. So, the light from distant galaxies hasn't even reached us yet. But that's only part of the puzzle. Next, we need to consider how the universe itself behaves. Picture this: the universe isn't static. It's not just sitting there, immovable and unchanging. Instead, it's in a constant state of flux, an endless dance of matter and energy. The universe is expanding. Now, what does that mean? Imagine blowing up a balloon. As it inflates, every point on its surface moves away from every other point. This is a helpful analogy for the universe's expansion. When we look out into space, we're seeing galaxies moving away from each other. This isn't because they're jetting off into the cosmos, but rather because the fabric of space itself is stretching. It's like they're on the skin of our balloon as it inflates, moving apart not through their own motion, but because of the expansion of the balloon itself. But what does this cosmic expansion have to do with our question, why is space dark? Here's where things get interesting. This movement of galaxies affects the light they emit. As a galaxy moves away from us, the light it sends out has to travel a longer and longer path to reach us. This stretching journey not only takes the light more time to reach us, but it also shifts the light towards the red end of the spectrum, a phenomenon we call redshift. Redshift is named for its effect on visible light, which moves the light's color towards the red end of the spectrum, the end with longer wavelengths and lower energy. This shift isn't just a color change, though. It also dims the light. The further away a galaxy is, the more its light is redshifted, and the dimmer it appears to us. So, the universe's expansion doesn't just move galaxies away from us. It also dims their light, making them less bright, less visible, and yes, making space itself appear darker. With galaxies constantly moving away and their light dimming, we begin to see why space isn't a blaze of light. Finally, we must consider the age and size of the universe. The universe, as vast and seemingly limitless as it appears, came into existence at a specific point in time. This is where the Big Bang theory steps in, a theory that proposes a finite age for our universe. The Big Bang, that colossal explosion of energy and matter, happened approximately 13.8 billion years ago. Now you might be wondering, what does this have to do with the darkness of space? Well, the finite age of the universe means that light, despite its incredible speed, has had only so much time to travel. Not all light from every star has had the chance to reach us. Picture this. Even light from our closest stellar neighbor, Proxima Centauri, takes a little over 4 years to reach us, and it's only 4.2 light years away. Now imagine the stars and galaxies billions of light years away. Their light simply hasn't had enough time to cross the cosmic expanse and reach our eyes. This brings us to another mind-boggling concept, the observable universe. The observable universe is essentially a cosmic horizon, the part of the universe we can see from Earth. Its size is determined by how far light has traveled since the Big Bang. The light from stars and galaxies beyond this horizon hasn't reached us yet, and perhaps it never will. So when we gaze at the night sky, we're only seeing a tiny fraction of the universe. The unobservable universe, the parts of the cosmos beyond our sight, could be teeming with countless stars and galaxies, but their light is yet to reach us, and until it does, they remain shrouded in darkness, unseen and unknown. So, the age and size of the universe restricts the light that has reached us, contributing to the darkness of space. So, why is space dark? Well, let's recap what we've learned. Firstly, light isn't instantaneous. It takes time to travel. That means we only see light from stars that have had enough time to reach us. Secondly, our universe isn't static. It's expanding, and as it stretches, the light from distant galaxies gets redshifted into wavelengths we can't see with our naked eyes. Thirdly, the universe isn't infinite but finite, both in terms of its age and its size. There are only so many stars within our observable universe, and only a fraction of those stars' light has had the chance to reach us. So when you gaze up at the night sky, the spaces in between the stars aren't empty. They're filled with unreachable light from distant stars and galaxies, redshifted and stretched by the expanding universe. The vast darkness of space is a reminder of the universe's grand scale, the limits of our observation, and the mysteries that await beyond what our eyes can see.